Welcome to the All Sorts podcast. It's the deep dive you know and love, where we wade through fascinating stacks of information, and we distill all of that down to that concentrated insight, just for you. Today, we are plunging into a fundamental phenomenon that powers a surprising amount of technology that is humming around us, often unseen. Thermionic emission. You shared some really excellent sources with us, articles detailing the core principles, the historical journey, and the diverse applications of this truly captivating effect. Our mission on this deep dive is to unpack exactly what thermionic emission is. We'll explore the mechanics behind it and reveal why it holds such significance, all while keeping our explanations clear and engaging.
That's good.
Think of this as your personal backstage pass to understanding this key player in the world of electronics and physics. And as always, guiding us through this intricate landscape is the insightful expert speaker ready to shed light on the core concepts and weave together the crucial connections.
Happy to be here.
So thermionic emission, it sounds rather grand. What exactly are we talking about? Let's begin to unpack this.
Well, the story of thermionic emission has a serendipitous beginning, dating back to 1883 with Thomas Edison.
Oh, wow.
So while he was experimenting with his incandescent light bulbs, he observed a curious current flowing from the heated filament to a separate metal plate inside the bulb. This unexpected observation became known as the Edison effect.
A chance discovery sparked by that iconic invention, the light bulb. That's a fantastic twist of fate.
It is indeed. And what Edison stumbled upon was the very essence of thermionic emission, the liberation of electrons initially termed thermions from materials when they are heated.
Wow.
This phenomenon proved absolutely vital for the evolution of early electronics and communication, becoming the fundamental source of electrons in those groundbreaking vacuum tubes. It was the bedrock of that entire era of technology.
So putting it simply, we're talking about heating something up to the point where it starts shedding electrons, like tiny sparks flying off a hot surface.
That's a vivid way to put it, yes.
Yeah.
The more formal definition is that by applying thermal energy heat to a metal, we cause electrons to be emitted from its surface. This is the thermionic emission effect in action. The name itself is quite telling. Thermionic combines thermal, referring to heat, and ions, which in this context specifically means charged particles are energetic electrons.
Okay, so heat coaxes electrons off metal, but what's the actual process at the microscopic level? How do these electrons break free from their atomic bonds?
Thermionic emission kicks in when metals are heated to very high temperatures.
Okay.
To understand why, let's first consider what's happening within a metal at a normal everyday temperature. The electrons in the outermost shell of the metal atoms, known as valence electrons, gain some kinetic energy and become what we call free electrons. They're constantly moving randomly within the metal lattice.
Like a swarm of tiny bees buzzing around inside the metal structure.
Precisely, however, at these normal temperatures, these free electrons don't possess enough energy to overcome the attractive pull of the positively charged atomic nuclei and escape the metal surface. You can think of it like this. The energy level of a free electron inside the metal is actually lower than the energy it would have in the vacuum outside. So they need an extra surge of energy to make that leap.
So there's an energy barrier, an invisible wall holding them captive within the metal.
A potential energy barrier, exactly. Now, when we intensely heat the metal, these free electrons absorb a significant amount of thermal energy. This increased energy gives them the necessary oomph to overcome the attractive force of the atomic nuclei at the surface.
And with enough energy, they simply break free and fly off.
That's right. These energized electrons that escape the metal's grasp and move into the vacuum are what we call thermions. This fundamental process is the key that unlocks the operation of a wide range of electronic devices.
That makes intuitive sense. More heat means more energetic electrons leading to more escaping. But are there other factors besides just cranking up the temperature that influence how many electrons are emitted?
Absolutely. Three primary factors come into play. The temperature of the metal surface, the total surface area of the metal, and a property of the metal itself called its work function.
Let's take those one by one. Temperature seems pretty clear-cut. Hotter equals more energetic electrons, so higher escape rate, right?
Correct. The higher the surface temperature of the metal, the greater the proportion of free electrons that will possess enough kinetic energy to overcome that surface energy barrier, and thus the higher the rate of electron emission. It's a direct correlation. More thermal energy available means more electrons can make the jump.
And the surface area, I imagine a larger surface provides more departure points for the electrons?
Exactly. If you have a metal with a larger surface area that is heated to a given temperature. You will have a higher overall emission rate, simply because there are more locations on the surface from which electrons can be emitted. Think of it as having more doors available for the electrons to exit.
Okay, and then there's the work function that sounds like a crucial property of the material itself. What exactly is it?
The work function of a metal is the minimum amount of energy an electron needs to have to escape its surface and venture into the vacuum.
Okay.
Think back to our analogy of the kids in the ball pit trying to get over the wall.
Okay.
The work function is effectively the height of that wall, a property determined by the specific type of metal and its atomic structure.
So some metals are naturally more electron-friendly, holding onto their electrons less tightly than others.
Precisely. A metal with a lower work function will require less energy input in the form of heat to liberate its electrons, resulting in a higher emission rate at a given temperature, compared to a metal with a higher work function. Interestingly, this work function isn't an immutable property. We can actually lower it by applying specific coatings, such as certain oxides, to the metal's surface.
That's ingenious, like making the escape route a little bit easier for the electrons.
A very apt comparison. Furthermore, there's a particularly interesting effect observed with cesium.
Okay.
When a thin layer of cesium is deposited onto a tungsten surface, it can dramatically reduce the work function, even to a value lower than that of pure cesium itself. This eutectic-like behavior, where the combination exhibits a property beyond that of its individual component, is a fascinating area of study in surface science.
Wow, that's a surprising little detail. So it's not just the inherent properties of the metal, but also how we treat its surface that matters.
Exactly. Now, to put a more quantitative framework around these relationships between the emission rate and factors like temperature and work function, we have what's known as the Richardson-Dushman equation.
Ah, the language of physics. Lay it on us, but please provide a bit of a translation for those of us who aren't fluent in equations.
The equation looks like this. J equals AT squared, x open parenthesis negative W divided by KT close parenthesis. Here, J represents the current density, which is essentially a measure of the rate of electron emission per unit area. T is the absolute temperature of the surface measured in Kelvin. A is a theoretical constant related to fundamental properties of electrons. W is the work function of the material. And K is the Boltzmann constant, which links temperature to the average kinetic energy of particles.
Okay, I recognize a few of those terms. What's the key message this equation conveys without getting lost in the symbols?
The most crucial takeaway is that this equation mathematically confirms what we've been discussing. The emission current density, J, is significantly higher when the work function W is low and the surface temperature T is high. The exponential term open parenthesis negative W divided by KT close parenthesis emphasizes just how sensitive the emission rate is to these two factors. Even a small change in temperature or work function can lead to a substantial change in the number of emitted electrons. A constant A has a theoretical value around 1.2 times 10 to the 6th amperes per meter squared per Kelvin squared. But in practice, the experimentally measured value can vary somewhat depending on the specific material and surface conditions. Some sources might even cite a rounded value like 600,000 A per meter squared per Kelvin squared. Think of A as a fundamental starting point that gets tweaked by the real-world behavior of different materials.
So the equation reinforces the idea that low work function and high heat are the prime ingredients for a robust flow of emitted electrons.
Exactly.
Now, this phenomenon bears some resemblance to something I've encountered before, the photoelectric effect. Are these two related concepts?
They are indeed related in that both involve the emission of electrons from a material's surface. But the crucial difference lies in the source of energy that triggers the emission. In thermionic emission, as we've thoroughly discussed, the electrons gain sufficient energy to escape by absorbing thermal energy. They energize by heat. This process typically occurs at specific temperatures, and the rate of emission increases as the temperature rises.
Heat is the driving force behind thermionic emission.
Correct.
What about the photoelectric effect?
In the photoelectric effect, electrons are ejected from a material when light energy in the form of photons strikes its surface. The energy for electron emission comes directly from these incident light photons. This effect occurs when the light has a frequency above a certain threshold specific to the material. And the number of emitted electrons, called photoelectrons, increases with the intensity of the light.
So light energy in electrons out in the photoelectric effect, whereas it's heat energy and electrons out in thermionic emission. Different energy sources leading to a similar outcome.
Precisely. Now let's move on to the fascinating realm of where thermionic emission finds its applications.
Okay, I'm eager.
This isn't just an abstract scientific principle. It's a workhorse in numerous technologies.
I'm eager to hear about the practical applications. Where do we encounter this hot electron action in our daily lives or in advanced technologies?
Well, historically, one of the earliest and most pivotal applications was in the development of vacuum tubes.
Okay.
These glass tubes, relying on thermionic emission from a heated cathode to generate a stream of electrons controlled by electric fields, were the fundamental building blocks of electronics for a significant period.
Okay.
They powered everything from early radio transmitters and receivers to audio amplifiers and the first electronic computers.
Wow.
Imagine a world without transistors. These glowing tubes, often the size of small light bulbs and generating a considerable amount of heat, were the engines of the electronic age, a real testament to early ingenuity.
So those iconic glowing tubes in vintage radios and old televisions, that's thermionic emission at work?
Absolutely. And while transistors have largely replaced vacuum tubes in many applications, thermionic emission remains a cornerstone in various modern technologies. For example, it is absolutely essential in electron guns, which are integral components of sophisticated scientific instruments, like electron microscopes.
Electron microscopes, the incredible tools that allow us to visualize the tiniest structures imaginable.
Exactly. Scanning electron microscopes, or SEMs, frequently utilize a hot filament, typically crafted from tungsten and heated to an incredibly high temperature, around 5,000 degrees Celsius, to generate the focused beam of electrons used for high-resolution imaging. In certain applications, this thermionic emission source is favored over other types of electron sources because it offers a cost-effective way to achieve high brightness, particularly for illuminating larger areas of the sample. So going back to our initial goal of understanding how this fundamental process powers our world, you can see how this seemingly simple idea of heating up metal to emit electrons leads to something as sophisticated as seeing individual atoms.
That's truly remarkable. From those early radio contraptions to the forefront of scientific discovery, what other applications rely on this principle?
Thermionic emission also plays a crucial role in the generation of X-rays.
Wow.
In an X-ray tube, a beam of electrons produced through thermionic emission from a heated filament is accelerated by a high voltage and then directed to strike a metal target. This collision causes the target material to emit X-rays.
So the same fundamental principle underlies medical imaging technology.
In part, yes. Furthermore, thermionic emission is being actively explored for direct energy conversion. Devices called thermionic converters can directly transform heat energy into electrical energy by harnessing the flow of electrons emitted from a hot surface to a cooler surface. This technology holds promise for efficiently utilizing solar energy or capturing waste heat from high-temperature industrial processes.
Wow.
Another intriguing application is in electrodynamic tethers used in space.
Oh, really?
These long conducting wires can potentially use thermionic emission to either generate electricity from the Earth's magnetic field or to provide a means of cooling spacecraft.
Space cooling using hot electrons. That sounds counterintuitive, but incredibly innovative.
It's a nuanced process involving the emission of charged particles into the vacuum of space to carry away energy. Closer to our planet, thermionic emission is also employed in arc jet thrusters, a type of electric propulsion system used for spacecraft maneuverability. The hot cathode tip within the arc jet emits electrons, which contribute to the electrical arc that heats the propellant-generating thrust. So it even helps rockets navigate the cosmos. This seemingly simple trick of releasing electrons through heat is far more versatile than one might initially imagine.
Indeed. And even in seemingly unrelated fields like ultraviolet light detection, low thermionic emission from the photocathodes of certain sensors at room temperature is actually beneficial by minimizing the spontaneous release of electrons when no UV light is present. It leads to lower background noise, improving the sensor's overall sensitivity. And let's not forget the historical significance. The Edison effect, that initial observation in the light bulb, directly paved the way for the development of the Fleming valve, the first practical diode. This crucial component was essential for the detection of radio waves, marking a real turning point in communication technology. It's all interconnected from a seemingly minor observation in a light bulb to the foundation of radio communication and a multitude of advanced technologies today.
It is.
It's astounding how one fundamental discovery can have such far-reaching consequences. Now, you mentioned electron guns earlier, and it sparked a question about controlling and enhancing this emission.
Okay.
Besides simply increasing the heat, are there other techniques we can employ?
Yes, there are indeed methods to enhance thermionic emission.
Okay.
One significant technique, particularly relevant in the design of electron guns, is known as Schottky emission, or field-enhanced thermionic emission. In devices like electron guns, a negative electrical bias is applied to the electron emitter. This creates a strong electric field at the surface of the material.
So an electrical assist to help the thermally energized electrons overcome the barrier?
Precisely, this applied electric field effectively lowers the potential energy barrier, the work function that the electrons need to overcome to escape.
Okay.
By reducing this barrier, it becomes easier for electrons to be emitted, leading to a significant increase in the emission current at a given temperature. This effect is mathematically described by a modification of the Richardson equation that incorporates the strength of the electric field.
That makes perfect sense. A little extra electrical encouragement for the electrons to make their escape.
Then there's an even more cutting-edge concept called photon-enhanced thermionic emission, or PEAT.
Okay.
This approach aims to synergistically utilize both light and heat, for instance, from concentrated sunlight to generate electricity. The idea is that the incident photons can excite electrons within the material, raising their energy levels and making it easier for them to subsequently overcome the work function with the aid of thermal energy. This combined effect has the potential to substantially improve the efficiency of solar energy conversion beyond what can be achieved with traditional photovoltaic methods.
Combining light and heat for a super boost of electron emission. That's a fascinating direction for future energy technology.
It's a very promising and actively researched area.
Okay.
Finally, it's important to remember that while our discussion has primarily focused on thermionic emission from metals, a similar phenomenon can occur at the surfaces of semiconductors. When a semiconductor is heated, charge carriers, either electrons or holes, depending on the type of semiconductor, that possess sufficient thermal energy can also be emitted thermionically into a vacuum analogous to the process in metals.
So the underlying principle of heat-induced charge carrier emission is a fundamental one, applicable across different classes of materials. And returning to a practical point, if one wanted to simply increase the rate of thermionic emission from a given material, without changing the material itself or drastically increasing the temperature, what would be the most straightforward approach?
Increasing the surface area of the emitting material is a direct and relatively simple way to increase the overall thermionic emission rate, as it provides a larger number of sites from which electrons can be emitted.
Simple and effective. So to summarize our deep dive into this topic, thermionic emission produces charged particles, specifically electrons.
Yes.
And it occurs within metals and semiconductors when they are heated to sufficiently high temperatures, allowing these electrons to overcome the material's work function and escape into a vacuum.
That's an accurate and concise distillation of the core principle.
So you see, this seemingly simple act of heating a material to release electrons is at the heart of a breathtaking range of technologies. From the historical vacuum tubes that laid the groundwork for our entire digital world, to the sophisticated electron microscopes that allow us to peer into the very building blocks of matter. Here's where it gets really interesting. The subtle dance between temperature, the intrinsic properties of materials, and even externally applied fields can profoundly influence this fundamental emission. This deep dive into the world of thermionic emission has, we hope, provided you with a much clearer understanding of this pivotal scientific principle.
I hope so, too.
What insights resonated most with you? What unexpected connections did you uncover as we explored this topic?
As you continue your own journey of learning and discovery, remember the profound power that lies in understanding even seemingly basic scientific concepts. These foundational ideas often underpin the very technologies that shape our modern world in remarkable ways.
Now, listener, as we bring this illuminating exploration to a close, we have a special invitation for you, our fellow traveler, on these intellectual adventures. If you've enjoyed this deep dive into the fascinating world of thermionic emission with the All Sorts podcast, and if the spark of curiosity has been ignited within you, we encourage you to nurture that flame. Head over to YouTube and subscribe to the All Sorts podcast channel. Give our videos a like and share them with anyone else you think might appreciate these journeys into knowledge. We have a whole universe of previous deep dives waiting for you to explore, each one a unique expedition into captivating topics. And please do connect with us beyond YouTube. You can find the All Sorts podcast on X, Instagram, and Threads. Follow us there for more insights and updates. Your engagement and support are what fuel our explorations and help us bring you more of these mind-expanding deep dives. Here's a final thought to ponder. Consider the potential breakthroughs that might arise from our increasing ability to manipulate materials at the atomic level, if we could precisely engineer the work function of materials atom by atom. What unimaginable new applications in energy generation, advanced electronics, or even entirely new fields might become possible by harnessing the controlled release of electrons? Let that idea simmer. And perhaps we'll delve into related topics in future deep dives. Until our next exploration, keep that spirit of curiosity burning bright.